And now officially, once again, bonjour, mesdames et messieurs. Welcome everybody to the second day of the Linux Audi conference. And it's the early morning session, so we're running a little bit late, but we'll try to catch up again. Our first talk this morning is by Dominique Faubé from Gram. I've been using a lot of software from Gram over the years, first MIDI-Share, then Faust, and finally InScore, a very nice program for doing interactive notation. And this is also what Dominique's talk this morning is about. So I won't read the title, it's up on the screen, I guess. And Dominique, take the stage, please.
So good morning, everybody. And so I will talk about InScore and about dynamic and animated music score. Actually, I will start with a few words about Gram research in the domain of music representation and notation. There are two main projects, InScore, which I will talk in more details. Another one, Guido. The Guido project is about software components for the layout of symbolic music score. And just a few words about Guido, because Guido is used by InScore, and so as to better understand what happens with symbolic score. And Guido project is based on the Guido music notation language, which is a simple textual description of music score. You have an example here. Yes, right. And the project comes with a lot of tools, an editor where you can type the music description, have real-time rendering of the score, a library with many interfaces, C, C++, Java, JavaScript library, etc. So, just InScore, Guido has been already presented in LAC 2009 and 2014. So now InScore is an environment for the design of augmented interactive music scores, and it supports symbolic music notation, the Guido format or music XML format, support textual elements. You can have pictures in the score, vectorial graphics, video files, and sound and gestures graphic representation. Actually, it's a standalone score viewer, an open source C, C++ library. It's multi-platform. It supports Linux, macOS, Windows, iOS, Android. And the system is designed to be controlled using Open Sound Control. So there is an OSC API and also an OSC-based scripting textual language. First presentation of InScore was in 2012. And but there are many new features that have been added to the system, and that's what I will present now. So the main issue addressed with InScore are, first, to have an open graphic and time space. Of course, every object of the score has a graphic dimension, but also a time dimension, meaning a date and a duration. So the system is able to make what I call time synchronization in the graphic space. It means that the system can represent the time relationships between the different objects of the score. It includes sound and gesture graphic representation viewed as signals. It supports interaction processes representation, which is quite poorly supported currently in the domain of interactive music. So it supports dynamic and interactive scores. That's the kind of things that I will show in more details. Network and web extensions, I will also show that. And symbolic score composition. So I will show you a short overview of the system. Actually, there is a video on YouTube that you can find on that you can find on InScore page, but I will use another one if I can find it. Yes, here it is. Okay. So the first example is dynamic symbolic notation. So here, in this piece, the computer computes both the piano. It uses Super Collider. It computes the piano part and also the score in real time that is displayed to the performer. I will just move quickly to the next example. This one is another use of InScore. Actually, the name of the piece is December Variation. And here on the right, you can see this more or less famous piece from Earl Brown that dates from 1952, I think, named December 1952. And it's a purely graphic score with no indication on how to play it and designed especially to break the traditional form of music. And Richard Hoadley made a variation of this on this piece, meaning that on the left you have a symbolic music score that is computed from variations of the graphic score, and everything is made using InScore, both the graphic score and the symbolic music score. So here you have a chrome pressed version of all the variations of the score. So this is to illustrate the performance representation. Here you have a signal, a graphic signal that is actually the a combined pitch and RMS representation synchronized to the score. Actually, the idea here is to transform the graphic of a signal into a graphic signal. And a graphic signal is a combination of 6 signals. The first one, the Y deviation. The second one controls the thickness of the graphic. And the other ones are used for the color. So the color model is hue, saturation, brightness, and transparency. And you can freely combine all these signals all together and so build, let's say, a very different representation using that. And it has been used in a piece named Line 9, where here it's a piece for harp and a dancer. The dancer is equipped with captors, sensors that are controlling both the music and the video projection. Okay, here time synchronization in the graphic space. How we do that? So the spine of the whole system is the time, and time is musical time, meaning time relative to a tempo, and where 1 is represent a whole note. So how do we do that? We do that with segmentation and relation between segmentations. And here we have a segmentation of the score and of the picture, and both are related to the time line. And we make composition, very simple operation. And we have a relation between the graphic space of the picture below, which is actually a score for Mark Applebaum, and the symbolic music notation on the top. And so we can just use this relation that is going through the times to display the graphic score in the context of music score. And if you change this relation, you change the way it's displayed on the other score. So this is an example of use with research of Pavlos Antoniadis, who is a pianist who is specializes very complex pieces from Xenakis, Ferneyhoff, and he's using a system with sensor and system for rewriting the music and to, well, it's a bit complex to explain all the things. So, an open graphic space. Here you have a picture and with a cursor synchronized on the score. Actually, it's a modeling of Tyrannus from John Trowning. And so you can change the representation. The sound is played by PD or Max MSP, and InScore is only displaying the score. And you can change the representation on the fly just by drag and drop of InScore script. This is another example of use where you have a very
secret love.
Actually, here the score is not a real score intended to be played. It's a piece for clarinet and computer, but it illustrates what happens on the computer side.
Has found out.
So I will skip this example too. It's another example of use. I will skip that because I will be back with the scripting language very quickly. You have event-based interaction, and so I will show also that. Symbolic score composition, I will show that more in details with concrete examples. And the last part. Okay, here, local and internet support. So you can, inside the score, you can put local resource, file-based resource, but these resources could be also fetched from the internet. So there is no difference. You can say, okay, this image is this file on my computer or on somewhere from the internet. And you can also embed a web server in the score, meaning that your score becomes available from the internet. And there is also a web API that allows to modify the score from a web browser. And there is also forwarding mechanism that is used to address several stations on the local network using UDP. So that's a quick overview of the system, and I'll go back to my presentation. Whoops. So I will show you some example of the scripting language. I assume you have a basic knowledge of Open Sound Control, and I will show you just some scripts. So the first one here, a very simple script, begins with a clean scene. It addresses the del message to all the objects of the scene. Next, we create a text object. We are doing some scaling, some positioning. We are setting the font. This is a type-specific attribute of the text. Here we create a rectangle. We adjust the color. Here we create a very simple score. And we have here some Guido code, some scaling, and here it is. You have a very simple score in a few lines. So let's say now that we'll add a cursor Actually, it's a circle. We set the color, and we synchronize the cursor to the score. Note that the message is addressed to a specific node, the sync node in charge of synchronization management. So when an object is synchronized to another object, X position is not free anymore. It corresponds to the date of the slave of the master. Sorry, but the Y position remains available, and we set the cursor to the tempo to 60, and the cursor moves in time. So I will show you quickly this example. So this is in score. Actually, the application has no user interface. And here it is. So now I will ask the cursor to watch time intervals. So the message here is watch something, an event. Here the events are time enter with interval 2, 3, and -1, 0. And when the event occurs, meaning that when the cursor enters these time intervals, these messages are triggers. So it means that actually it invert the tempo, set it to negative or positive depending on the time interval. So up, and here it is. This is my example. And so I can drag and drop files, but I can also drag and drop text directly. Here I set the tempo to 0. So I will add a simple text that we use as a controller. That illustrates the mechanism of events interaction. So this is a command. We set text, a text, and we ask the text to watch mouse events, mouse enter, mouse lift, and we associate color changes just for feedback to the user. And we ask the cursor to watch mouse down events. On mouse down, it sets the tempo to 0, it sets the text to start, and it sets a new behavior so that on next mouse down, it's changed the tempo to 80, set the cursor, change the text, and the whole in a loop because all the interaction state can be pushed and popped from a stack. So it's not sure that I have this. Yes, here it is. Okay, stop, start, and etc., etc. Well, just to illustrate how it works from network dimension. So there are some specific messages that you can address to scenes or to the application level. So load, okay, understand what it means. You load an in-score file or an in-score bundle. Root path set the current path in case the relative path is used for file resources. But so when it's like the PWD in a Unix shell. So when you say root path is user me in-score and you say the scene load myscore.inscore, it refers to users me in-score / myscore.inscore. But if you set the root path to HTTP somewhere, it refers, the same command refers to http dot, etc. And the forwarding mechanism works the following way. You address the message forward with an IP address or a host name, and so that you can forward all the messages to another station or a group of stations or to the same station on a different port. And you have also filters where you can specify the kind of messages you want to send or to reject. That's all. And now I will show you a demo of various demos of symbolic score composition, network and web support, sensor, time model. So, symbolic score composition. So, very simple example here. It's not this one, okay. This is a very simple example where the cursor is moving in time like in the previous example, but each time it reached the end of the beginning of the score, there is a circular permutation of the score that that is made. And this is done using the score composition operation. Oh no, that's not the thing. I didn't want that. So the expression is, it's not this one, yes, okay. So the expression to do that is the following. Just you have an expression that put in sequence the tail of the score. The score is the object score. Score composition is very consistent. You use a score. It takes two scores as each operator takes two scores as argument to produce a new score as output. So on a duration of 7 quarter notes and tail score, okay, and the head of score on the same duration, and that's all. Another example with a combination of, okay, here I have a combination of a static and dynamic score. Actually, I'm computing on the top left. A random score is computed each time I click on write. And this random score is next combined with a static score that is the lower line of the score in the middle and transposed to the first note of the two last bars of the dynamic score. And how that works, not that one. Okay, actually, this script is making use of free score. R score is, let's say, the real-time score. C score is the composed score, and there is also a hidden score named P score. So I will show this score. This hidden score is used as a temporary object to just to cut the last two bars of the real-time score. And what happens here? We are just asking the real-time score to watch data change. And when the data change, it sends the message expression re-eval to the P and C score. The C score just expression put in parallel the p-score with a transposition of a static score with a to p-score. And p-score is just the tail of the r-score taken after the tail of r-score. Let's say it takes the two last bars. So this is for score composition. Next part is okay, the web dimension. Okay. Okay, this score makes use of remote resources. So you have a symbolic music notation score that comes from inscore.gram.fr, a graphic score from Wikipedia, and a picture also from Wikimedia. And so I can publish this score, so embed a web server. And here it is. I have another score that embeds this one and combined with other local resources. And now I can as well use a web server. Okay. And browse this score from the web server and even modify the score. Okay. Up. Voilà. Here it is. So maybe I will just change the position. Okay. This is for the web dimension. Now for the local network dimension, I will use my phone and just to illustrate that. So I will here okay, I will. Okay, Marco Polo is my my computer, and I just check. Yes, that's okay. I will just send. I'm using here extended OSC address. This is the address of my mobile. So, and I will ask my mobile to forward all the messages to my computer so that you can see something. And now I will, for example, demo effect. My phone is Oui. Non, non, mais sur, je suis connecté sur mon téléphone directement. So I'll do it again. I think there is something wrong with okay, so last attempt, otherwise. No.
I'm using the local network because the ports will be closed.
Ah.
The 7,000 port should be open. So
oh my God. So I was wanting to demonstrate also the sensor object because, yes, okay, because with the mobile version you have, so each time I ask my phone to forward the messages, it freezes, and so I don't know what to do. I can't debug right now in the 10 minutes that left. So I will skip that, so it's really pity. And non, je suis connecté en mode AP, là, access point sur mon téléphone. Ben ouais, peut-être éventuellement, mais le temps que je me configure et tout, mais on peut essayer. Ouais. Okay, so I will show you other examples. This one. This one illustrates the fact. So, I guess now we have understand that you can ask an object to watch events and to watch events in a time domain. And so, in a given way, let's say I just used mouse events and time events, but events typology includes any object attributes, and you can also define user-defined events. And here, with this example, I have three objects, three cursors synchronized to three circles, and in a given way, I've put messages in the time domain, and each cursor makes a circle and activate the tempo of the next one, etc. And I will just show you. Okay. So the first one, C1, when it leaves a given time interval, it sends the message tempo to C2 using its own tempo. It sets its own tempo to 0, and etc. So the line on the bottom illustrates what happens on the time and what are the messages that are sent during each time interval. So in a given way, you can use the system just to put messages in a time domain. So I'm try to make a last attempt. So you say that, and it's opened. Okay.
The universal fast access point.
Okay, I'll try. Uh-huh. No, so I think I will waste the time because I need an IP address, a real one. I'm not sure that I. Okay, so let's go to the questions. Last thing. So INSCORE is an open source project. You can find it at very recently it moves from SourceForge to GitHub, and well, so that's all. Thank you.
Thank you very much, Dominique. And well, the demo effect, we've had quite a bit of that yesterday as well, so it's always there. So are there any questions? We surely have time for one or two.
Actually, I would like to have two questions. The first one is it possible to extend the score in real time? So you have a musical score and add notes, for example, in real time?
Yeah.
Okay, so then it's just
Depending, of course, on the score complexity. If you want to have a symbolic music notation, and if you want to have real time with a 30 pages score, for example, it starts to be a bit longer to compute. But
so then it's redrawn, or is it just shifted?
to redraw the score in real time,
Yeah.
yeah.
Okay. And the other question is, how do you? So if you have a score for real-time performance, how do you handle the latency between reading the score and performing the score?
I think here in this domain, the latency problem is really different from the audio domain because the eye has not the time accuracy that the ear first. And actually, how that works, actually the system is, there is a time task that by default run every 10 milliseconds. So normally you have a 10 milliseconds delay, maximum delay if you want to, between the message and the display. Does it answer to your question? No.
Not exactly, because I mean, I was rather thinking of if you perform something together like a real musician and a computer-created score, the computer can handle sound immediately, so you have the latency of the sound card and stuff. But
yes,
the musician has to read the score and plan some kind of actions. So the musician itself has its own latency.
yes,
Which is much longer, probably more in the domain of tens of milliseconds.
yes, but I'm not sure to really understand the issue. Okay.
Okay, maybe we can discuss this later on. Some more questions? One more, maybe? Okay, Dominique, then thanks again.
Thank you.